Okay, hello everyone. My friends, Pat and Ben, sent me a link to a nice website that I want to tell you about. You can get to it very easily by just Googling the scale of the universe 2. And this is the website. And it shows you different scales from very small to very large, starting at the smallest with something called the Planck length. And you can just click on these things and it tells you about them. So I'm going to let my grandson tell you about these things. This is Charlie.
Starting with quantum foam, there's which is 1 times 10 to the 25 meters. That according to the space-time theory, quantum foam is also known as space-time foam. It is the quantum foam, which is also known as space-time foam, is the foundation of the fabric of the universe. It is impossible to directly observe or measure this because it is so small. According, this string is 1 times 10 to the 35th meter. According to string theory, when strings are one-dimensional but vibrate in all the other dimensions. The string, however, is not the same string you use for flying kites. That string is between 10 to the 32nd and 10 to the 34th times larger. Planck length is 1.6 times 10 to the 35th power. The Planck length is a unit of length. There is also a Planck time, which is the amount of time it takes light to travel 1 Planck length in a vacuum, super short. The neutrino is 1 yoctometer, which is 10 to the 24 meters, and then it has, neutrinos pass through the ordinary matter like you and me all the time. In fact, they're doing it right now. Neutrinos have no charge, so they are only affected by gravity and the weak force. However, they are so small that they are barely affected. Top quark is 100 yoctometers. 1 times 10 to the 22nd meters. The top quark is the smallest quark, which means it is the most massive. It is almost 100,000 times as massive as the up quark, which is the lightest of quarks. The top quark's mass is 173 billion electron volts. Now we have the high energy neutrino, which is 15 years. A zeptometer is 10 to the 24th meters. The high energy nucleus is 15 zeptometers, which is 1.5 times 10 to the 20th meters. The nucleus with higher energy are larger. For more about nucleus, go to nucleus, which shows the average size. It's a whopping 15,000 times more. The bottom quark is 30 zeptometers at 3 times 10 to the 20th meters. The bottom quark is also called the beauty quark because it is so flawlessly beautiful. It is the sort that erases and quickly decays into the first generation quarks like up and down. The top quark is 100 zeptometers, or 1 times 10 to the 19th meters. The top quark and the strange quark are the second generation of matter. They will quickly decay into up and down quarks, which are the first generation of matter. The term quark is charming. The strange quark is 100 zeptometers, or 4 times 10 to the 19th meters. Strange quarks are very strange. They are 50 times as massive as up quarks, but are still similar. Isn't that strange?
Shall I talk a little bit?
Very much so. Strange matter is made of up, down, and strange quarks. Let me get to finish with these quarks.
Okay.
The up quark is 1 atometer, which is 10 to the minus 18 meters. There are 6 flavors of quarks. They are up and down, strange, top and bottom. The smaller a quark is, the more mass it has. As a result, the up and down quarks are actually the lightest of quarks. This quark has a source of 2 thirds. And the down quark is also 1 atometer. There are 6 flavors of quarks. They are up, down, strange, top, and bottom. The smaller a quark is, the more mass it has. As a result, the up and down quarks are actually the lightest of quarks. This down quark has a charge of minus 1/3.
So, as you can see, my grandson's been talking about very small things, but this website, again, you can get to it by going to the size of the universe, the scale of the universe, 2, doing a Google search. This is the range of the weak force, which is part of the standard model of physics, which, quite frankly, I don't understand. The weak force is one of the 4 fundamental forces of nature and is the weaker of the 2 nuclear forces. The distance increases as its strength increases. As the distance increases, its strength increases, which is unusual. Decreases, which is usual. At just 10 atometers, the weak force is so weak that it is unmeasurable. Now, I don't think we should keep going. We should just tell them.
Then let me try. I want to keep on going.
We don't want to go.
Now 100 atom. This is one sorter than this are not conformed. This is 100 atometers, or 1 times 10 to the minus 6 meters, to the minus 16 meters. It only objects that are smaller than this unmeasured than this are unmeasured. The sizes that they appear are only estimates. Some things like or this type of the size. They aren't fact. A proton is 1 femtometer, which is 10 times 1 times 10 to the minus 15 meters. Protons are found within an atom's nucleus. They are thousands of times smaller than the atom itself. They have 2 up quarks and 1 down quark. Therefore, the proton torr is plus 1 divided by 3 plus 2 divided by 3 minus 1 divided by 3 equals plus 1. And then the neutron is 1 femtometer 2. Neutrons are found within an atom's nucleus. They are thousands of times smaller than the atom itself. They have 2 down quarks and 1 up quark. Therefore, the neutron's torr is minus 1 divided by 3 minus 1 divided by 3 plus 1 divided by 3 equals 0. And then the helium nucleus is 3 femtometers. 3 times 10 to the minus 15 meters. Helium nucleus is thousands of times smaller than the atom, like a marble on a football field. The only reason the matter feels solid is because atoms repel. If atoms don't repel, everything would fall together, would fall through each other. And that's it. This one I'm not going to go any farther. And if you would like to take this out, go to the search for the scale of the universe. I'm not leaving a link. And we might have a part 2. So we've done with a review